So our next speaker, Dimitrios Schoinianakis, Senior Security Researcher at Bell Labs. Dimitris is a distinguished member at Nokia Bell Labs. He has authored over 25 papers and books on secure systems. From secure hardware to the future of cryptography, he is helping build the safety nets of our digital world. So thank you for being here.
Thank you, Lena.
Yeah, thank you for being here, Dimitri. His speech is about security in the quantum era. I will let him give the speech, but I want to say again, I was telling him before, I'm very excited. He's come all the way from Bell Labs, the birthplace of C programming language and other important inventions. So yeah, we're excited having you.
Thanks
the
so
stage
much,
is yours.
Thanks
A
so
warm,
much.
warm applause.
Good evening. So I've been thinking that if we had this exact same discussion 6 months ago, I would be probably not have included a couple of important slides for some EU Commission mandates that were published just recently. 2 or 3 years ago, I would be probably talking about some cryptographic algorithms that were, in the meantime, badly broken in a simple laptop within a weekend. And maybe 4 or 5 years ago, this whole discussion about quantum and security would be for many completely irrelevant. I guess what I'm trying to say is that this weird intersection of quantum technologies and security brings us in a kind of muddy kind of situation. So from that point of view, I think we have an excellent opportunity that we meet up today to clarify a few things. Now, we tend to split the timeline of quantum innovations into two main eras. What we call quantum technology 1, basically all the way back at the beginning of the last century, up until the 1950s, 1960s. That's when we started understanding the ensemble behavior of particles, atoms, electrons, photons, and so on. But the key word here is assembled. So we were interested in the collective behavior of these, of atoms and electrons. And it wasn't until the 1950s and 60s that we saw a big bulk of innovations, fundamental innovations like the transistor, LEDs, the lasers, the basic principles for MRI. Actually, many of these are attributed to Bell Labs' Nobel Prize-winning works back then. And then what is of interest to us, of course, is how we shifted to quantum 2. So we moved from the assembled behavior to actually fiddling with particular particles, so specific atoms and electrons. And now we have the ability to operate on individual quantum systems, and we are able to harness these very quirky and very weird properties of quantum superposition and quantum entanglement. Obviously, this is not a quantum computing session, so I'm not going to go into details on that. But that's the big shift, from assembled behavior to quantum, to specific individual quantum systems. And because of that, we can now build quantum circuits, and to an extent, on those quantum circuits, we can now build and run quantum algorithms. And this is what has given rise to the three fundamental technologies: quantum computing, quantum communications, and quantum sensing. Obviously, our interest is quantum computing. For quantum communications, I'm going to touch briefly on that. Quantum sensing is a beast on its own. Basically, in 2 words, quantum technologies will allow us super accurate measurement capabilities. For example, think of GPS in the range of a few centimeters, if not more, if not less, sorry. Potential applications of quantum computing. First of all, anything that can be expressed as an optimization problem is very well prone to quantum computing. Simulations, this is of particular interest for example, the pharmaceutical industry. We will be able to perform simulations, for example, on large molecules that it's beyond our capacity, our computational capacity reach nowadays, battery design, and many others. As for AI ML, this is really exciting because, and I'm not really an expert on the ML front, but I'm not talking about running your traditional ML workloads on quantum computer. Now we are talking about something fundamentally different. I'm talking about new quantum algorithms that can actually run ML or AI workloads. It's a very exciting field. And unfortunately, and this is not a potential, it's more of a problem and the reason we meet today. Unfortunately, for us in the cryptography and the security domain, large-scale quantum computers, as we will see, can and will crack almost all of the foundations of our modern security. Some of the leaders in the development of quantum computers have also already started coming up with the basic architectures as to how these wonderful machines will be embedded into our digital infrastructure. Just as an example, IBM, they came up with this architecture. So basically what you have here, those silver boxes, is your quantum computer alongside with the necessary infrastructure like refrigerators to cool down these machines. And then the black ones are your typical data center racks where you will have normal workloads, maybe even some error correction, as we will see for the quantum computers. And then you see this networking fabric that needs to be in place in order to interconnect the quantum with the traditional data center infrastructure. PsiQuantum's architecture is basically the same. This is an important diagram here. So in our quest to build a large enough quantum computer that can actually do meaningful things and solve really, really difficult problems for us, we need to solve two things. So on the x-axis, you see the number of logical qubits. Qubits, it's just the fundamental information unit, the equivalent of bit. And so what we want to do is we want to increase the number of logical qubits so we can run more complicated algorithms. But at the same time, on the x-axis, we want to reduce the errors that come up as you try to pack more and more qubits on a single chip. That's due to quantum phenomena. It's due to physics. So this dashed line also, by the way, it's very important. It crosses the x-axis up to something 60 qubits. Everything on the left corresponds to algorithms that can run perfectly fine on traditional computing environment. So our effort is basically to pass this dashed line and move on to the region on the right where we will see the true supremacy of quantum computers against classical computing infrastructure. Right now, for example, 2025, 2026, IBM, as one of the leaders in developing quantum computers, they have now packed a couple of hundreds of qubits on a single chip. But it's interesting to notice that they no longer, I presume for technology reasons, they no longer pursue packing more and more qubits, but rather they want to have a modular architecture, so basically interconnecting many of those single chips into a kind of networking mesh in an effort to increase the number of logical qubits. But that's exactly where we want to go. We're going to go on the top right-hand side of the picture with thousands of logical qubits and very, very small error rates, because that's where we will unlock all those nice applications. But unfortunately for crypto, that's when cryptography will be broken, as we will see. A quick wrap-up for those who are not, let's say, into crypto. I'm going to be quite brief on that. The foundations of security of our digital economy, I could say even, is due to these very small algorithms in the area of symmetric cryptography. That's your fast AES encryption algorithm. It's symmetric because A and B that try to talk, they use the same key, a symmetric key. And then the question is, okay, how can we derive this same key on both parties? Well, there are different ways. You can have pre-shared keys, like in your SIM card. We can have quantum key distribution, which is actually part of the quantum communications we mentioned before. I'm going to touch on that briefly. But by far, the most popular way is through asymmetric cryptography. So another type of crypto, you don't have symmetric keys there. You have public and private keys. you exchange the public ones, and through the use of clever mathematics embedded in our well-known protocols like TLS, IPsec, VPN, and so on, you come up with a private key, and then you plug this into asymmetric algorithm. Now, the problem with quantum computers is due to a gentleman called Peter Shor. By the way, Peter Shor was working in Bell Labs back then when he developed his algorithm. And because of Peter Shor's algorithm, all the mathematical foundations of our modern asymmetric crypto should be considered broken. So I'm talking about your RSA algorithm, elliptic curves, the digital signatures, the lot. I would also like to debunk a kind of myth. In the past few years, due to another algorithm by Love Grover, incidentally also in Bell Labs at the time, it was perceived that Love Grover's algorithm impacted symmetric crypto as well. And so the general consensus was that we need to shift from 128 bits to 256 bits. This is perfectly fine for even today's security standards, and we will see that, of course, happening. But it's not that it's a threat. Love Grovers is not a threat to symmetric crypto, and so for applications like, for example, in constrained environments, it's still perfectly fine to use 128 bits. Now, I guess many will say, give us a break. You tell us something like 15, 20 years' time until we see a large enough quantum computer. Why are we discussing this now, right? It's a problem of today. I could even say it's a problem of yesterday. So the problem is this harvest now and decrypt later threat. And think of this like this. Assume you want to offer some kind of secure product or some kind of secure service for X years from now, and you allow yourself Y years until you deploy some kind of quantum safe strategy, whatever this may be. And then let's also assume that in Z years from now, we have this large enough quantum computer that can break our crypto. Then there is this famous inequality by Professor Mosca, which says that if those X plus Y is greater than Z, then you have an issue. What this inequality basically tells us is that every day we are losing today during those Y years by not deploying some kind of quantum safe strategy corresponds to data being revealed in the future once a quantum computer becomes available. And obviously, this is very pertinent for data with long confidentiality. Think of military applications, government, medical, and so on. And so another way to formulate the question is, what do we do today and how we can minimize this Y time frame until we develop and deploy some kind of quantum safe strategy? And that's the bitter truth, I guess. Our ICT industry prepares now, as we speak, for this major migration from traditional crypto to something new, which we will see in a couple of slides. And this is an exercise that hasn't been done before to such an extent, and it's a very complicated one. So how quantum security will look like in the quantum world? Well, symmetric, as we saw, symmetric solutions will be there, no problem at all, apart from the fact that we will probably increase the keys, but this is perfectly fine. What now happens is that we need to replace the broken crypto by Peter Shor's algorithm with something new. And this something new, it's called post-quantum cryptography. It's just a new family of cryptographic algorithms that are based on different mathematical problems which are conjectured to be secure against quantum computers. This is also something not known to many, not in the crypto domain. There is no formal and rigorous mathematical proof that what we use today is secure. It's just that no clever scientist has found a way to crack those algorithms. And the same thing happens with these new post-quantum algorithms. But other than that, our public key infrastructure, our authentication mechanisms, our key agreement protocols will remain mostly the same. Obviously, they will need to be adapted to accommodate these new algorithms, but they will be mostly the same. Who develops these algorithms? Well, no surprise, NIST, the National Institute of Standards and Technologies. They started this effort 9 years ago. And after many elimination rounds and many algorithms that were broken, we came up in August 2025 with 3 standards, one for key exchange and 2 digital signatures. And for backup reasons and other reasons, actually, there are 2 more algorithms to be released and standardized soon. Then IETF picks up this work, and they are currently producing the next PQC drafts. We expect to have those ready by the end of 2025. And as for other standardization organizations, which I guess this discussion is more pertinent to the telecom sector, 3GPP, ITU, and ORAN, they will be developing their own standards, but in most cases, they will be following the recommendations by NIST and IETF. That's the slide I mentioned at the beginning. So we have to admit that the EU came in a little bit late into the game of PQC. We had a large focus on quantum key distribution in the last couple of years, and it wasn't until April, I think, last year, when we had the first set of recommendations from the EU Commission towards the member states, and this was actually the updated one in June this year. And now we have actual timelines on an EU level on how to proceed with the migration effort. So these are just some milestones that it's useful to keep in mind. By 2026, the member states should have developed their initial PQC roadmaps, and they should also have developed the transition planning for medium and high-risk profile cases. By 2030, the transition should be completed for high-risk cases, and the transition planning for medium cases should also be complete. And something very important, when it comes to quantum-safe software and firmware signing and secure boot sequences and so on, post-quantum crypto also needs to be in place by 2030. 2035, obviously, everything needs to be PQC ready. Now, a few words on quantum key distribution, because it's a very hyped and kind of sexy technology. So quantum key distribution is just another way to achieve a shared encryption key on 2 ends, okay? It operates over a single fiber channel, and it's based on quantum physics. It's not based on mathematics. However, quantum key distribution does have its own limitations. So we can only support up to a few tenths of kilometers. We now study satellite QKD to circumvent this problem. But apart from that, there are also some security implications. So if you want to cover larger distances, you need repeaters in between. And these are security holes in your end-to-end connection. Also, the single fiber line is not enough. You also need a traditional authentication channel. So many will say, come on, we use traditional crypto anyway, so why do we use QKD? But it has its own use cases, understandably, especially for data center interconnectivity or government applications. And it definitely has its own piece in the post-quantum pie, if we could say that. Moving on specifically to networks, there are 2 main threats on our networks. One's the threats that target our data, and this is the harvest now and decrypt later problem that we saw. So basically, intercepting encrypted data today and deciphering them once a quantum computer becomes available. So we need to be able to protect our data and user plane. And then there is attacks against the network functionality, so mainly focusing on your control plane, your management plane. But these are not yet faced today because these require the presence of a large enough quantum computer. On the other hand side, we saw that the standards are not there yet. So 3GPP hasn't developed the standards yet, for example, for mobile networks, right? So to address the user plane, we might need to wait a little bit more. But in the control and management plane, we don't have such a strong hinge on the standards, so we might have the luxury to already start implementing PQC earlier. Now, the root of trust, I think it's basically it's the baseline of security, even when it comes to networking equipment. I'm pretty sure, we're in a kind of software venue here, so we all know what the root of trust is. You have your code, you have your encrypted hash of the code, and then When you want to do the verification, you compute a new hash, you decipher the one that you have received, and you compare those. If these match, great. So these operations need to support post-quantum crypto, as we saw. And just to highlight how important this is, CNSA 2.0, CNSA is the Commercial National Security Algorithm Suite. It's a kind of policy, a kind of mandate published by the US administration. And there you will see that they have very strict guidelines. And actually their top focus, it's not shown that well, their top focus by 2030 is software and firmware signing. That's what the US wants to protect first. And this is, I guess, well in line with the timelines that we saw before for the EU. There are a couple of problems, and actually this is a shout out to HSM providers and TPM manufacturers to support PQC early enough. The problem is that we have PQC, but we also have another nice construction called hybrid post-quantum crypto. Hybrid is nothing more than a clever combination of traditional and post-quantum crypto in one scheme. So think, for example, of TLS. You have a hybrid TLS. 2 sessions, 1 key, which is a combined version of a traditional session and a post-quantum session. Now, the problem is that there is no regulatory, there is no consensus on a regulatory point of view. So some might follow a hybrid approach. In the US, for example, they said that they will go straight towards pure PQC implementations. And we see this split up also in the EU and in other parts of the globe. I don't want you to even try to have a look at this slide. I only brought this up as a kind of teaser because this is a very nice example from the network domain as to how complex this exercise of migration from traditional to post-quantum will be. So this is a full-blown end-to-end 5G system, all the way from your user equipment, your access networks, your core network, user plane, management plane, the lot. All interfaces you see on this slide need to be migrated. So basically the full ecosystem needs to migrate. And this is just an example to highlight how complex this will be as we move on. And obviously, this is the job that we now currently do in standards to push for post-quantum solutions. With regards to the migration, some companies were actually early enough into the game. So already by 2022, IBM started introducing PQC in some of their AI platforms. I think what made quite a sense last year was the introduction by Apple of PQC algorithms in their iMessenger, I think it's called. And remember, we are talking about non-standardized algorithms. So why did they do that? They did that because it's the best practice. You want to be proactive and test how these algorithms impact your system. And it's actually now that we progress and we gain more maturity into this migration journey, it's actually quite clear who are going to be the early adopters of these technologies. And the early adopters are going to be privately managed networks. I'm talking about government applications, critical infrastructure, the financing. So the banks are very interested in post-quantum solutions. And then, as the standards also mature, we will see those technologies into public networks. Some key some kind of takeaways, let's say, that we can take with us. And I mean, if you ask yourself, what can I practically do? Is the most important thing is actually start creating your cryptographic inventories, your cryptographic assets. It's very important to understand what type of crypto you're using, where and in which configuration. And obviously, this is not, I mean, networks are not a kind of monolithic structure. So depending on your function and your operation, you can have different inputs. For example, if your work hinges on industry standardization organizations, you should start studying the security aspects of standards and, if possible, create inventory of those needing attention, and why not push solutions into the standards and enable a better harmonization. If you're more on the software and hardware domain, that's where the notion of cryptographic bill of material comes into the game. You know this much better than me. A cryptographic bill of material is just an extension of a software bill of material, so just a well-structured layout of what type of crypto I'm using, which parameters, and so on and so forth. So once you have those inventories in place, you should be able to collaborate better with your third-party providers, your vendors, and come up with a migration strategy. And that's only if you know very well what type of crypto you're using. And on the operational domain, this can, a C-bomb or an asset in general can be very well leveraged on network scanning tools, for example. So think of being able to show whether you are compliant or not with regards to post-quantum safety and provide your inputs to migration strategies. And obviously, when it comes to full transparency towards regulatory bodies and policies, you should be able to prove that once you have your assets in place. So, really create a project team to have a look at your cryptographic assets and evaluate your cryptographic stance and posture, right? And what needs to be done as you move along. And that's also something that we all need to keep in mind, is that whatever we do to replace our current crypto, this needs to be under the notion of cryptographic agility. Cryptographic agility simply means that I am able to replace, swap, update my cryptographic algorithms without disrupting the underlying infrastructure. Why? Because it took us almost 20 years to gain confidence in the algorithms that we are using today. And so we expect that with these new algorithms and these new mathematical constructions, it will take us lots of time until we gain this confidence. And until then, cryptanalysis is still very active. Like I said, algorithms were badly broken that were out there for like 20 years, and this happened just 2 or 3 years ago. So whatever you build in your software stack or in your hardware stack, make it work in an agile fashion. To wrap up, I think it should be clear by now that the quantum threat is real and it's imminent and it's happening now. Migration has already started. States now have a mandate, for example, from an EU point of view, to move on with their migration plan. And also remember, quantum computing advances is not just the one pathway to break your algorithms. The other pathway is with better quantum algorithms requiring less qubits. So we can live with less powerful quantum computers running Peter Shor's algorithm, as an example. And also always take in time that these migrations take lots of time. And so a quantum-safe network is really the outcome. It's not a single technology. It's a layer of technologies. This is maybe for the first time in our ICT industry that we have a golden opportunity to do this right, because cryptographic failures have happened, and they've been catastrophic, but now we do have the opportunity to set a golden standard when it comes to migrations of this type and protect ourselves in the quantum era. Thank you very much for your attention.